All right, so today we'll start by reviewing homework. We'll have a somewhat abbreviated lecture just because of the fact that we also have to do course of valves, because I've been postponing that. It has to happen at some point. And then quiz as well. So someone, or more than one someone, when it gets to be 10 after 2, we need to stop so we can do the evals and the quiz. Okay, so remind me if I, for some reason, am continuing to go. All right, so let's talk about the homework. How many of you guys have worked on the assignment? I know I've seen about 3 people who've submitted it. Has anyone else worked on it? All right, 4, so on. Okay, very good. So it is interesting just because the assignment is related in some sense, because you're solving the same problem of creating an LSTM that solves the parity problem. But in one case, you're doing it, you know, scratching your head, pencil and paper. In the other case, you're training the LSTM. And they're pretty different ways to approach it, I would say. So, so this is interesting if I'm going to do it, because I don't quite remember what my solution is. So let's see. So there's a hint, thank goodness. So the hint is XOR is equivalent to A and not B, or not B and A. A and not B, or not A and B. And can we use that when updating CT in equation 4? So let's figure out what the heck CT equation 4 is. So this is just the update of C sub t, right? So C sub t is composed of a combination of C sub t minus 1 and a calculation of based on the old h and the old x, right? So how much of C sub t minus 1 do we use when we're computing C sub t in an LSTM? And let's make sure I'm getting fully randomized here. Sally. Tim's not here. Santi. F sub t, right? So this is the forget gate calculated at time t, right? Because remember, the forget gate has a different value for every time t. And so that is our value here that we're going to do a Hadamard product with our old C sub t minus 1. So by all rights, this should be R sub t. It's a remember gate. How much of it are we remembering it? But we're using it in the opposite sense. So it's a forget gate. If it's 0, that means we forget it. If it's 1, that means we don't forget it, right? Plus then another gate. Matt, what's the next gate we use here? Yeah, I sub t. So this is the input gate, right? How much of the stuff that's coming in goes into C sub t. And that's basically our activation function, which in this equation is tan h, right? That's what we're using. Could be something different, but that's what we're using. So tan h, and then we're going to have our traditional x sub t w x. Did I call it xh? xc? xc, makes sense. Plus then our old h sub t minus 1 w hc plus some bias. Yes? So the hint says XOR is equivalent to this. If we look at Boolean logic, often ORs are pluses, right? And ANDs are more like multiplication. So could we treat this as something like A and not B, and this somehow as not A and B? And this like an OR. Does that make sense? And so if we're trying to do the XOR of x sub t with XOR of 1 to x sub t minus 1, right? That's really what we're trying to compute at each step, yes? We're trying to say we want c sub t to be equal to the XOR of the current bit along with the XOR of the previous bits. So if that's the case, then this is c sub t minus 1, right? Kind of in an induction step. So we assume that's c sub t minus 1. So let's call, so this is B, and here is A. So we want this to be this is A, and this is B. This is going to be B and not A. So this has got to be A and not B. So how can we make f sub t B not A? F sub t is not x sub t. Do you agree that'll get this partial part of it? So we know we've got x coming in. We've got a matrix. It's a 1 by 1 matrix. So this is WXH. We've also got HT minus 1 coming in. Do we care about HT minus 1 in computing f sub t if we want f sub t to just be not x sub t? We don't care, so therefore what would we make this matrix? We make that one B0. So what we've got to play around with is basically we've got f sub t equals sigmoid of x sub t WXH plus XF plus BF, right? Because we're making this one B0. So we want this to be 1 if x sub t equals 0, and 0 if x sub t equals 1. So I'm thinking there are going to be some negative numbers in here somewhere. So if we make WXF equal, let's try negative 1, then this is going to be, if x is 0, that'll be 0. And if x is negative 1, this will be, sorry, if x is and so if we add 1, we get 1 and 0. That is, if it's a 1, it turns to 0. If it's a 0, it turns to 1. So therefore, that says to me, this weight matrix should be negative 1, and this bias should be 1. And for simplification, we said that the sigmoid is going to be 1 if this is greater than 0, and is going to be 0 otherwise. So I suppose this is just any number greater than 0 for the bias would work in this case. Any questions on that? I'm not fully convinced by you guys, by the lack of questions. So convince me. Well, we know there are infinite solutions for what the bias could be, because it's any number greater than 0. Actually, this doesn't have to be negative 1 either, necessarily, right? This could be a negative number in combination, but I think you'd have to have one of these be a negative number.
But could you make it like somehow only dependent on h sub t? x of t, so I'm just wondering if there's any specific way. Or does that always have to be set to 0?
Well, so here's what we know. I don't think so, and here's why, but let me just think about this a second. So the dependency from x of t to c is from x of t to c sub t to h sub t, right? So x sub t goes into c sub t, goes into h sub t. What else do we know? We know that h sub t looks like a gate O sub t times tan h of c sub t, right? Yeah? So h sub t has this indirect dependence on x sub t, but it's pretty indirect. And so I'm not sure how you could do it. If you did it in your homework, I'm going to have to look at it and think about it, which I don't like having to think about, but I'll try thinking about things.
Yeah,
but
it's what I eventually got to, but I think I checked it.
Okay, well, I'll check it. It's possible. It's possible.
I did it in a totally separate way than this, so I could have been
Okay.
on track.
This will make probably this homework much more challenging to grade than some previous ones have been. Okay, so this is my approach, and yeah, there may be other approaches. So the next approach is to say that let's make I sub t equal to x sub t, and this thing equal to not c sub t minus 1. Right, so basically we've got this is not x sub t, and this is c sub t minus 1, and this is positive x sub t, and this is not c sub t minus 1. Yeah? If we can satisfy that, and we satisfy a base case, that is, we want to make sure that c sub 0 is 0, I guess, then we'd be okay. So let's see what we can do easily about this. We want I sub t equal to x sub t. Well, I happen to know this is the formula for I sub t. I know there's also a WHI, and I'm going to say I want that to be 0 because I don't want to depend on h. And so what would our weight matrix be? Rory, what we'd use as a weight matrix here if we want I sub t equal to be x sub t. Okay, identity matrix, which for a 1 by 1 is really simple, right? That's just that matrix. What would the bias be? 0, sounds good. Couldn't be anything else, actually, right? Couldn't be any other bias, because otherwise, if x were 0 and we got 0, but then we added a bias, then our sigmoid would take us to 1, and we don't want that. So I think this is what it has to be. Does that make sense? Now we get I sub t equals x sub t. Yeah.
Maybe I'm a little behind this, but we're just looking at the h of t minus 1 equals 0 case, right? Because from the
No. So far, no. So far, nothing we've done relies on what h sub t minus 1 is.
Okay, we're going to just look at them because we have the equation that you give us in the notes does have like an h of t minus 1 term.
But we've said WHI equals 0 and WHF equals 0. So therefore, we don't care.
Okay.
That's how we got around that.
Okay.
Okay? And the reason for that is we wanted this to just be not xt, this be xt. We don't care about any dependence on h.
Yeah.
So the final one is now we want this sucker to be c sub t minus 1. We're out of the gate business for now. So we want this whole thing to be not c sub t minus 1. Well, we don't want this to be a negative 1, right? Because that certainly wouldn't be not anything in Boolean logic. So therefore, this thing better not be less than 0. We want this thing to either be equal 0 or greater than 0. And that will take the tan h to be equal to either 0 or 1. Do we care about x sub t? No, because it says this is c sub t minus 1. We only care about the last time step. We don't care about this time step. So wxc equals, Willow? It's 0 because we don't want the current value of x to interfere with this part, because we're trying to make it not c sub t minus 1. Okay? So now we're left with tan h of ht minus 1 whc plus bc. And if this is 0, it'll be 0. And if it's greater than 0, it'll be 1. So we want, right, we want that. Well, I guess this is dependent on h sub t minus 1, right? So this had better be something useful for us. We will have some control over what this is. We haven't done it yet, but we will have some control over it. What would it be handy if this were? Ben.
C sub t minus 1.
If this were c sub t minus 1, you can see how we'd get there pretty easily, right? So let's just assume, for the moment, h sub t minus 1 equals c sub t minus 1. Okay? In that case, then, it's again just doing this not problem, right? So in the not problem, Brandon, how could we do that? What could we choose for WHC and BC?
The same thing as previously.
Yeah. And that was?
Negative 1 and positive.
Yeah, let's say positive. Does that make sense? Are there questions? We still haven't done this. We'll need to do this. So we now have weight matrices for the C matrices, WHC, WXC, BC. The F matrices WXF, WHF, and BF. The I matrices WXI, WHI, and BI, and we're left with one more set of matrices. Josh, what matrices are those that we're left with? Okay. We've got 3 gates, the forget gate, the input gate, the output gate, and we've got these computations of C. We already dealt with the computations of C, we dealt with the input gate, we dealt with the forget gate, so that just leaves one more gate, the output gate, right. So the output gate controls, again, h sub t, which is good, because that's what we're trying to make sure we can set this up. So h sub t equals the output gate with the product of tan h, c sub t minus 1. What do we know about tan h of c sub t minus 1? Nick?
The equation we have here says tan h c sub t.
Good, thank you. This will make our life easier. In our simplified version of tan h, if c sub t is 0, what's tan h of c sub t?
0.
And if c sub t is 1, it's 1. So, well, let's say this is just the same thing as c sub t. So, Rachel, what do we want O sub t to be if we want h sub t equal to c sub t? Sorry, h sub t equals c, yes, h sub t equals c sub t.
1.
Yeah, so we want this to equal 1. So now we can come up with our matrices to make that equal 1. So our two matrices are WXO, WHO, and our bias, BO. What would be good values for these, Rachel? If we want O sub t to always be 1. So this is sigmoid of, set it to what?
1.
And what about these guys?
0.
Sounds good to me. Does that make sense? Any questions? I thought about, although I did not, after training, so doing the assignment, the last assignment, and training, looking to see what these biases and weights were and see if it's in any way close to this. If someone wants to look at that and compare those, I think it'd be interesting. Any questions?
What is the formula for O sub t again?
O sub t is, yes, I brought a little bit of it. So it's just like all the other gates. So it's x sub t and then the associated weight matrix. So WXO plus, and then we take the h from the last time step, h sub t minus 1 WHO plus our bias. Yep. All right. All right, so a couple of things to talk about. The two main things I wanted to talk about were multi-layer RNNs, which I think I mentioned just briefly on Wednesday, but I want to talk about them just a little more. And then also talk about a little more about using RNNs to generate data. So using, for instance, a language model to generate sentences, for example. So if we look at, I don't know, a regular old neural network, right? We've got some input. We've got layer 1, layer 2, layer, I'll call it L. Let's just make it a CNN. Just for fun, okay? So these are convolutions. At layer 1, what sort of features are we picking up? Anyone? Yeah, low level. Low level features. And at the other end, we have high level features. So we're taking an advantage of the fact that at successive levels, we can group together combinations of lower level features from the previous level, right? So take the raw input, extract some features, build features that are composed of those features, build features that are composed of those features, and so on throughout. We don't get really the same power if we have an RNN. Okay, if we have an RNN, the way that I've been writing it, horizontally like this, we actually had our input coming in from the bottom, right? And as we go to the right, these are not layers. These are time steps. So this is, right, time step 1, 2, 3, all the way to some time step, we'll call it t. Right, x1. So there's only a certain amount of power we've got in here. We basically got one neural network layer that we're operating in here on our input. So what's contained in here is sort of a low-level feature based on x. And then we move to the next, and we're not building more sort of on, not quite building more on top of x. We are augmenting our history now with our x2 and our x3 and so on. It'd be nice if we had not only this temporal calculation, but also we had sort of this calculation as well, which is more spatial. And so the way to do that is go in 90 degrees from this way. So if we have time steps going horizontally, let's go ahead and have layers going vertically. So we are going to, let's say here, we're going to have a multi-layer RNN. And when I say an RNN, it could also be an LSTM or a GRU. So we'll have our X come in here. And again, as we go horizontally, I'm just unrolling this, right? Time step 1, 2, all the way to t. So this is x sub t, is our input here. I'm going to put these little boxes to show that we have a matrix multiplication there. We have our h coming in here, which I'll call h sub 0. And I'm going to call h sub 0 super 1 because it's the first layer. So the output here is going to be h sub 1 super 1 because again it's the first layer. All the way to coming out of here, h sub t super 1. The h's also go through this matrix. And I'm going to get rid of our y matrix here. And in fact, I think I mentioned in Keras that y matrix is separate. So you have to explicitly provide that y matrix. So we're going to feed h not only to the right, but also up. So h, 1, 1 is going to come up as well, and that's going to be the input into a separate RNN. I'm going to make it separate and kind of showing, I don't know how to make it separate exactly. We're going to mark this and say this is separate and this is separate. This could have 10 hidden units. This could have 100 hidden units. If this had 10 and this is 100, how big is this matrix right here? Mo?
For a big number.
Yeah. So let's say we have TID and UDs here, and we have 100 here. And my question is, how big is that matrix here?
The one that's going up.
The one that's,
The one that's taking. So it's going to should be 10 times 100.
it'd be exactly 10 times 100. Yes. In fact, this is almost to scale, sort of. At least it's wider than it is tall. So this would be 10 times 100 because it would be taking a vector of size 10 to a vector of size 100.
I actually have a question.
Sure.
What's the kind of layers that we're using for RNN? Is it the connecting layers or is it a new kind of thing?
They're RNN layers. So it's just one RNN feeds into the next RNN, feeds into the next RNN, and so on.
And so when you say that, like, different types, steps are separate from each other, does that mean that when we batch propagate, that when we edit the weights of one time step, it doesn't affect the next one?
That's a good question. Let me finish putting this. I'll put the loss up, and then we'll do just a sample backpropagation to one particular time step. Okay, let's see if that explains that. So this is H sub 0, 2, right, coming in here. Maybe different size than H sub 0, 1, even though they might both be zeros. This input is H sub 2 super 1. The output is H sub 2 super 2. The output goes both up and to the right. And eventually, we get to the top RNN. Okay? Our architecture choice is how many of these RNNs we choose to stack. Right? Maybe 3, probably not 300. So this, let's just use L for the same value here. It's the number of layers we have. These are the number of layers we have, all of which are RNNs. So coming out of here is H sub 1 super L, and coming out of here, H sub 2 super L, and so on. Let's say we just have a single classification problem that we're solving here. So all we care about is this H L, no, H sub n super L. We go ahead and feed that through a matrix and through a sigmoid, and that gives us y hat. Our entire y hat, right, is we run all these time steps and layers, and when we get to the eventual, here's our output. And then we have some loss based on y hat and y. Okay? Yes?
I have a quick just kind of vocab question. When you say hidden units, do you mean number of weights and all the matrices combined?
What I mean is how big is the vector H? Okay? Just like if we're in a regular neural network, right? And I talk about the size of a layer. That's, again, how big is the vector of all the values there. Okay. And which is going to be one of the dimensions of the matrices, that both the input matrices and the output matrices. So if I come and look through here, let's say I look here. Okay, I'm interested in this particular time step and layer because I want to be updating maybe the weight. Where can I have loss coming into here? Can I have loss coming in? Is there a path through the up arrow? In fact, there are many paths, right? One path is up, 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 and then all the way to the right, and then up and out to the loss. Or I could go up and over and up and over. There are a lot of such ways. Or I can just go directly right and over. But certainly, in order to calculate the loss correctly here, or rather the gradient of the loss, I would need the gradient of the thing to the right and the thing to the top. And I would need to sum them together. Is this hitting on your question, Mo? Okay. And remember, as we're dealing with these shared weight matrices in an RNN across time steps, we need to basically calculate what's the gradient of the loss with respect to the weight matrix at this time step and at the previous time step and the previous time step and the previous time step. We may stop with this truncated backpropagation, but however far back we go, then we're going to go ahead and average that gradient to update the weight matrix. Anisha.
Why is this better than doing an RNN or CNN? Like, I understand that we're combining this idea of like time and layers.
Here's the idea. This layer can be calculating low-level type features, and as we go up higher and higher in our layers, it can be calculating higher and higher level features about our sequence of input. In the same similar way, we have higher and higher level features.
During the forward propagation step, does it go all the way through all the layers like vertically and then step over one, or does it kind of do it like simultaneously?
How does it do it? How is it actually implemented? It could do it either way. And I believe in Keras, it does it this layer first and then this layer. Because in Keras, when you define an RNN, right, you create an RNN, and by default, all you get out is the last H. But you can also say, I think it's return sequences. Whoever's done the assignment already knows this. If you set that equal to true, then it returns the vector of H's. So RNN return sequence equals true returns a vector H1 all the way to H sub t. And RNN by itself with the default returns just H sub t. So if you're stacking, this is not enough, right? If you're stacking, you need to make sure that your layers, every layer but the top layer, always returns all the sequences. So basically it gets all the H's, and then those can be used as the input to the next layer, all the H's, and you'll end up then with, so you'll have RNN, return sequences equals true, you'll have some set of those, and then you'll have a final RNN without that return sequences equals true, and then you'll do one dense layer. In our case, if we have only a single output, it'll be a dense 1. And we'll have to put an activation either in here or here to say for this case sigmoid. And now that I think about it, it probably always is going to do the layer by layer, because if you have a bidirectional RNN, it needs to see the whole sequence before it knows what the values are to go up. So, questions on this? Okay, so it's just providing a more powerful network at a given time step. Because what we had at a given time step was a pretty simple network. And this just provides more power because we can keep building these combinations of the lower level features on top. All right, let's talk about sequences. Generating sequences. So let's say we have a simple model. I'm going to do words, but we could also do this on characters, where we're going to just predict the next word given the words we've seen so far. So we'll have sequences of words, and we'll feed them in. Let's say we look at a particular sequence of words as one single training instance. Okay, so it's going to be something like this. Let's say it's this. I am the walrus. Okay, we're using Beatles lyrics, let's say. Okay, so we're going to feed that in. And we're trying to train our network. So our R and N, we're going to feed in first something just to tell it we're starting. And then it is supposed to spit out y hat sub 1, which is a probability distribution over what's the next word. That is, if we're just starting a Beatles lyric, what are the probabilities of the first of the words? Right, so we get out some softmax across all words. We have our h sub 1. To begin with, we have a completely uninitialized neural network. Can we say anything about which word would be most likely? Not really. Maybe it's kangaroo, right? I mean, I don't know. Should we pick the most likely one and then feed that in here? No. We want to feed in I. So we're going to say, we're going to give you I. And now it's going to come up with its best guess for the next word. If this is early in its training, that's going to be pretty garbage probability distribution, right? So we're not going to pick what that word is. Again, we're going to just force it and say, no, I don't care what you think the probability is. I don't care what the probability of M, which is the next real word, is. I'm going to feed you in M here. And we're going to get y hat 3 and so on. So this is called teacher forcing. That is, in each step, we're going to force you and say, I don't care what your guesses have been so far. I'm forcing you to say, no, the input is I, the input is M, the input is the input is walrus. And so on. And now let's look at what is our loss function going to do. We have what do we want the probability, what is y1 with this particular training instance? That is, what is the correct y1? It's I, right? It's the one hot where I is 100% probability and everything else is 0% probability. So if we look at the loss with this particular training instance, we're going to look at the loss of kind of I against y1 hat. That's sort of loss of 1. What would be a good loss function to use for this? Comparing two probability distributions? Like we do when we're doing classification? Categorical cross entropy. Yeah, cross entropy would be good. So, cross entropy. And then we want to add in a loss for the second word. So we want it to be M And it's not actually the string I, right? This is the probability, the one-hot encoding of I. The one-hot encoding of M compared to what it came up with as L2 plus L3 plus L4. And what the heck should L5 be? We know we're comparing against Y5 hat, but what do we want it to be generating? End, exactly. We want the special end symbol that says these lyrics are now over. You can stop singing. Because the Beatles, I don't know if you ever have small siblings or something, but this is the song that never ends. Right? It goes on, and so that one never generates end. Okay. Does this sort of make sense? So we are predicting, for instance, in Y4, what is the probability of a particular word given all the previous X's that we've seen. So given that we have already seen starting I am the, what's the probability of the next word? That's what we're trying to learn. And this is one of our training instances for that. There may be other parts, other lyrics, you know, in Beatles songs where there's an I am the and it's not walrus that's next. But that's okay, the neural network will have to learn that. So we train this all, and eventually we hope we have a nice either single layer or multi-layer recurrent neural network that has a low loss, that is able to make these predictions.
I think I'm sold because how this setup of the teacher forcing is like different than maybe what we've done before with this. Because isn't it, we've always had like, you know, X of something, like our input at that, you know, particular time step, you know, and we're feeding in like a, you know, when we had the Wikipedia articles, there's like each character that was going in that. Was it not, like, how was that different than this?
That is not different. In some of our RNNs, we didn't care about these Ys. In some of the RNNs, the Ys weren't in some sense trying to feed back. Okay? We're going to talk a little bit more now about, let's say you get this fully trained, how can we generate random new Beatles songs? Okay? And that may make that clear, but it is just like what we're doing with Wikipedia. So, just to be clear, that the total loss is the sum of all these. So let's just say I want a new Beatles song, okay? So I am going to feed in to my neural network that's already trained. I'm going to feed in start. And I'm going to get out a y hat sub 1. It's a probability distribution over the first word for Beatles songs. I have a couple of different choices of what I do with that. I could do a greedy choice. Pick the most likely word. Okay? I don't know what it is. Let's say it's love. Okay? And then I would feed in here love. I cut out y hat 2. I could then take the greedy choice and say, well, what is the most likely word given that what we've seen so far is love? And I could just continue that on. Now, what question I got for you? Let's say I do that. I'm going to get some lyric, and eventually I'm going to get to end, and there it is. There's my lyric. And I say to you, this is sort of my greedy choice of what the most likely, what I think, given this greedy choice, what the most likely Beatles lyric is. What if I run it again? What do I get? Same thing. And if I run it again? Same thing. It's completely deterministic. Not very interesting. in that way. So how can I add some non-determinism? Ezra. I've got this probability distribution here, right? I know for every word what's the probability that it is the next word to use.
You could have like a probability that it'll use the highest probability.
What if the probability that used the highest probability was the highest probability? And the probability that used the second highest probability was the second highest probability.
It's just like softmax.
Yeah, so the softmax gives me the probabilities. They sum to 1. I could just use that probability distribution and sample from those words. Does that make sense? So I might get love is, let's say, 30% likely. And she is 20%. And I don't know in other words. There's others, but they're less likely, okay? And so I roll my dice and pick, and 30% of the time I am going to get love. But then and so in which case I'd feed love in here. But then I get another probability distribution, and I use that probability distribution, and I choose. So we're not going to get the same thing every time. Yeah.
What would stop us from just, so maybe for the very first one, we're greedy, we pick the first word, but then at each successive time step, you just feed in the entire softmax as input. So you feed in something that was 30% love, 20% she, and then you get a 30 output at that point, instead of just randomly sampling something. You're just giving the entire probability distribution.
Okay, so let's say I do that, and I get a bunch of, so then this would be an output probability distribution, another probability distribution. You're saying that we'd feed this directly in here, rather than sampling. I've got a bunch of probability distributions. What are my lyrics now? So that's the problem, right? So does the greedy make sense as opposed to the sampling? So what I can do then is, let's just, so until I get an end, what I want to do is x sub t equals argmax of y hat I minus 1. Argmax gives me, right, not the maximum value, but the maximum, not the maximum probability, but the word with the maximum probability, right? So which algorithm is this? We've seen 2 so far. Greedy, yeah. Go ahead. Yeah, this one's greedy. And we now have the sort of distribution model, which is until end. And by end, what I mean is x comes out as an end, right? Then we want to say x of t equals choose from y hat I minus 1. And by choose from, I mean choose weighted based on the probabilities. That's really the only difference between these two. Let me add one more thing we could do. And that is, let's say I want to know how would a Beatles song end if it started, I was going to the store. I don't believe that's the beginning of any Beatles song. So I want to know, I want a song that starts out, I was going to the store. I would basically say, for either one of these, x sub 1 equals start. X sub 2 equals x sub 3 equals was, x sub 4 equals going, and x sub 5 equals, to the store. And then I start the loop of seeing what gets generated. So I have preconditioned my RNN such that it is set up so that the first words are what I chose, and then it gets to go from there. Does that make sense, that idea? So you can set up these prompts, sort of.
So really, what you're doing with, if you just give it like, when you say you want to see like, what, given that the lyric starts this, what does it end with? You're basically just running through a whole simulation of things based on what you already have trained.
I already have a trained model, and I'm going to just feed in, I was going to the store, and then start using start sampling from the probability distributions I get.
Okay.
Okay. Yeah.
Is this functionality built into TensorFlow, or is this something that you need to build out a little bit?
You have to build it out a little bit, yeah. I don't, there may be some contributed, TensorFlow 1.0 had a contributed package, although that's been gotten rid of in 2.0, so there may be something there, I'm not sure. But it's not actually a lot of code.